Welcome back to the deep dive. I was thinking about how much we just take for granted.
Oh,
You
absolutely.
sit down, open a laptop, type a URL, and boom, the world's knowledge is there. It feels instantaneous. It feels, I don't know, like magic.
It really does. Magic is a good word for it.
Yeah.
Or maybe a high-stakes obstacle course.
Right. That's what this source material suggests. We're looking at a visual guide today called Navigating the Network, Packet Survival and Recovery. And that word survival really jumped out at me.
It should.
We think of the internet as this, passive cloud, but this guide paints it as a pretty treacherous landscape.
It is. I mean, every time you click a link, you're essentially birthing a data packet.
Huh.
And that packet has to go on this journey through a hostile environment, hop across different machines, change its identity multiple times, and try to avoid, getting dropped into a black hole.
So it's not just plumbing.
Not at all. It's an adventure story.
And that's exactly what we're going to do today. We are not just talking abstract networking theory. We are going on a rescue mission. We're going to follow the life, the potential death, and the rescue of one single network packet.
I love this approach.
Yeah.
And we have a specific topology from the source material to work with.
Let's set the scene for everyone. So visualize this. We have a source computer, PC1.
Okay.
For the note takers out there, its IP address is 172.16.3.10, and it has a mission. It needs to send data to a destination computer, PC3, which is sitting way over on the other side of the network at 192.168.10.
So PC1 to PC3, a 172.16 network to a 192.168.
Exactly. And standing between them is not just a single wire, it's a gauntlet. We've got three routers, router 1, router 2, and router 3, all linked together in a chain.
Like pearls on a string. But, and this is crucial, the string changes material halfway through.
What do you mean?
The connections between these routers aren't the standard Ethernet cables you plug into your wall. Between router 1 and 2, and then 2 and 3, we're using serial links.
Serial links. That sounds industrial.
It's foundational technology. It's a point-to-point connection. Think of it less like a modern highway and more like a dedicated pneumatic tube.
Okay. I do.
And that changes all the rules for how data moves.
Okay.
It's going to matter a lot when we try to get this packet across the finish line.
Okay, so the stage is set. Our brave little packet is sitting at PC1. It's ready to leave 172.16 half 30 point Lumview. Before it even steps out the door, we have to talk about identity. The source makes a huge deal about the difference between layer 3 and layer 2.
And this is where a lot of people get tripped up.
Yeah, my brain usually starts to hurt right about here.
It's simpler than it sounds if you use the right analogy. Think of the packet as a letter you're mailing.
Okay.
Inside the envelope, you have the letter itself. On that letter, you've written the final destination. I am going to PC3 at 192.168.2.sizzle.
And that's the layer 3 address, the IP address.
Correct. That IP address is the North Star. It is written on the packet at the very beginning, and it never changes.
Never.
No matter how many routers it touches, that destination IP is immutable. It's the ultimate goal.
Okay, so that's the letter. But you can't just throw a piece of paper into the wind. You need an envelope.
Exactly. You need a vehicle. That's layer 2. That's the frame. And unlike the letter inside, the envelope changes at every single stop.
So router 1, let's call him R1. He gets this packet from PC1. He looks at the North Star address.
The 192.168.2.0.
Right. And he realizes, I can't throw this all the way to PC3 myself. That's too far. But I do know my neighbor, router 2.
So R1 has to encapsulate that packet. It puts the letter into a new envelope addressed specifically to router 2. But this is where that serial link detail we mentioned comes roaring back.
Because it's a tube.
Because it's a tube. On a normal network like Ethernet, you're in a crowded room. You need a specific name, a MAC address, to know who you're talking to.
Right.
But on a serial point-to-point link, it's just R1 and R2. There's literally nobody else on the line.
So you don't need a name tag.
You don't. The source guide points out this really fascinating technical quirk here. On that serial link, the layer 2 frame destination isn't some complex hexadecimal code. It's just listed as broadcast.
Just broadcast.
Or all ones in binary. It's the digital equivalent of just shouting down the pipe.
Yeah.
You don't need to say, hey, R2, because R2's the only one who can possibly hear you.
I love that. It's so efficient. Just get in the tube.
And it does. R1 encapsulates the packet in this generic broadcast frame and shoots it over the wire.
Success. The packet has survived leg 1. It lands at router 2.
The middleman.
Now, R2 is the middleman here, and I think people assume routers are just like pass-through devices. They just bounce the signal. But the guide breaks down R2's logic, and it's much more active. It calls it Strip, decision, rebuild.
It's a processing factory. R2's doing actual work.
Let's walk through that factory line. Phase 1, strip.
R2 gets that frame coming out of the serial tube. The very first thing it does is tear it open. It strips off that all-ones broadcast envelope because that envelope's job is done.
It's trash now.
It's trash. It got the data to R2. So R2 is now holding the naked packet, the letter itself.
Okay.
Right. And now comes phase 2, decision. R2 looks at that North Star IP, the 192.168.2.0, and it has to consult its own brain, which we call the routing table.
It's checking its map.
It's checking its map. It's asking a very simple question. Do I know how to get to the 192.168.2 network?
And assuming we're on the happy path right now, where everything works, the map says yes.
The map says, yes, I know that neighborhood.
Yeah.
To get there, you need to go out the back door via serial 011.
Which leads to phase 3, rebuild.
R2 creates a brand new layer 2 frame, a whole new envelope. It puts the packet inside, seals it up, and sends it out the interface towards router 3.
Wow. And this strip check rebuild process happens for every single packet, thousands of times a second. It's not a continuous flow.
Not at all. It's a series of distinct handoffs. That's the hop-by-hop reality of the internet. Layer 3 directs the full journey, but Layer 2 only cares about surviving the next 5 feet.
Okay, so R2 hands it off to R3. The packet travels down the second serial tube and arrives at router 3. We're getting close now. PC3 is the target. But the landscape shifts here, right?
Drastically. We are leaving the cozy private world of serial links and entering an Ethernet network.
Because PC3 isn't connected by a serial cable, it's plugged into a local network.
Exactly. And Ethernet is what we call multi-access. Remember our tube analogy?
Yeah.
Ethernet is not a tube. Ethernet is a crowded cocktail party. Router 3 is standing in a room with potentially hundreds of computers, printers, phones.
So R3 can't just use that all-ones trick anymore. If it just shouted, "Here's the data," everyone would get confused.
It would be total chaos. R3 needs to be specific. It needs to deliver this packet directly to PC3. But here's the problem. R3 knows the logical address, the 192.168.2.S where, but it doesn't know the physical address.
So it knows who it wants, but not where they're standing in the room.
Precisely. This is the mapping problem. How do you map the software address to the hardware address? The network uses a protocol called ARP Address Resolution Protocol.
Yeah, I see this on the diagram. It looks like a call and response.
It is. So R3 checks its pocket first, its ARP table. Have I talked to this guy before?
And if the answer is no,
If the answer is no, R3 has to find him. So it steps into the middle of the cocktail party and shouts, literally broadcasts, who has the IP 192.168.2.0? Tell me.
and since it's a broadcast, everyone in the room hears it.
Everyone. PC1, PC2, the smart thermostat on the wall, they all process the question, but they check their own IDs and go, nope, not me, and they just ignore it.
But PC3 hears it.
PC3 perks up. Hey, that's my IP. So PC3 replies, but only to R3. I am 192.168.2.90, and here's my MS address.
And only then, once R3 has that specific ID card, can it build the final frame and deliver the packet.
That's right. A very polite, structured conversation just to deliver one piece of data.
So that's the symphony. When it works, it's beautiful, but we are here for survival and recovery. And usually right when you need to send that important file, the symphony turns into just .noise.
Entropy is real. Networks are dynamic. Cables get kicked, power supplies fail, and people, well, people make mistakes.
The source lists a few common reasons: interface failure, ISP connection drops, link oversaturation. But my favorite is human error.
Misconfiguration. It's almost always the culprit. Someone typed a 1 instead of a 2 or just forgot to tell a router where to go.
And this is where the guide suggests a total mindset shift. When things break, the administrator has to stop being an architect and start being a detective.
I love that framing.
Yeah.
You aren't building anymore. You're investigating a crime scene. Who killed the packet? Where's the body?
So let's put on our trench coats. The guide gives us an administrator's toolkit. 5 commands. First up, the most famous one, ping.
Ping is your heartbeat check. It's the most basic tool, but it's vital. It sends a tiny probe and just asks, are you there? If you get a reply, the patient is alive.
Next, traceroute.
That's your footprint tracker. It shows you every single hop the packet takes.
Yeah.
It tells you exactly where the delivery truck stopped moving.
Showed ripper.
That's looking inside the router's brain. Does the router even know how to get where you want to go?
Show IP interface brief.
That's checking physical reality. Are the lights on? Is the interface up? You'd be surprised how often it's just a loose cable. Layer 1 troubleshooting.
And lastly, show CDP neighbors.
That's a Cisco one, but it's so useful. It's like looking out the window to see who's standing right next to you. It confirms your physical connections.
Okay, detective, we have the tools. Let's work the case. The source provides a specific case study labeled Destination Unreachable.
Here are the facts. A user on the network reports they cannot access the 192.168.2.0 network. That's PC3's neighborhood.
So we log into Router 1, we try to ping the far end, 192.168.2.1. What happens?
Flatline. The source says success rate is 0%.
Yeah.
But, and this is a cute insight look at the error message, it says destination unreachable.
Why does that specific phrase matter so much? Why not just request timed out?
Great question. Request timed out usually means the packet got lost somewhere along the path or on the way back. It implies a path exists, but it's blocked. Okay, destination unreachable is way worse. It means the router is telling you, I have absolutely no idea where that is. I don't even have road on my map that goes in that direction.
Wow. So timed out is a silence. Unreachable is a hard rejection.
Exactly. So we know the path is fundamentally broken. Step one is isolation. Where is the knowledge gap?
So R1 tries to ping the next guy in the chain, R2.
And that ping is a success. R1 can talk to R2 just fine.
Then R1 tries to ping R3.
Fail.
Aha. So we can get to the middle router, R2, but we can't get past it. The fault lies beyond R2.
Correct. We've isolated the fault domain. It's R2. So now we have to examine the evidence. We need to check the routing tables.
This is step 2. We look at R1's routing table first.
R1 looks innocent. It has a static route entry. You see that little S?
Mm-hmm.
That means an administrator manually told R1 to get to 192.168.2.1. Go to R2.
So R1 is doing its job.
Perfectly. It's handing the packet to R2. So now we move to our main suspect, R2. We run show up road on it. And what do we see?
The smoking gun.
The smoking gun. R2 shows its directly connected networks, the ones it's physically touching. But when we scan that list for our destination 192.168.2.0, it's missing.
It's just not there.
It's a black hole. R2 gets the packet from R1. It strips the frame. It looks at the destination IP. It checks its map. The map is blank for that entire area. So R2 does the only thing a router can do.
It kills the packet.
It drops it immediately. It doesn't guess. It doesn't ask around. It just deletes it and sends that unreachable message back to the sender.
That is so brutal. It really highlights how literal these devices are. If it's not on the table, it simply does not exist.
Exactly. The logic is binary, known or unknown.
Okay, so we found the problem. R2 is missing a route. We need to perform the rescue.
This brings us to the configuration step. We have to manually add that missing route into R2's brain.
The source gives us the exact command string. It is EP route 192.168.2.0.255.255.255.192.168.1.1.
Looks like gibberish, but it's actually just a sentence, a set of simple instructions.
Let's parse it. What are we actually telling the router?
The first part, 192.168.2.0, is the destination. We're saying, hey, R2, if you get a package meant for this neighborhood.
Okay, destination.
The second part, 205.255.255.0, is the subnet mask. Think of this as defining the size of the neighborhood. It tells the router exactly which IPs are part of that group.
Got it. Destination, then size. And the last part, 192.168.1.1.
That is the next hop. We are telling R2, if you want to reach that neighborhood, hand the package to this specific guy. And in this topology, that IP address belongs to router 3.
So it's literally giving directions to get to the mall, which is this big, turn left at the gas station.
It is that simple. Once you enter that command, the routing table updates. The entry is now installed. The black hole is filled.
And the moment of truth, verification, we go back to R1 and try that ping again.
And this time, success rate is 100%, 55.
Those little exclamation points on the screen, there's something so satisfying about that. It's like watching a flat line turn into a heartbeat.
It is. It validates the logic. We isolated the problem, verified the evidence, and applied the fix. That's the core loop of network engineering.
You know, taking a step back from the command line, digital survival really is the perfect name for this deep dive.
It really is.
Because you can boil it down to 3 pillars, right? First, packet logic. The fact that routing is hop by hop. No one controls the whole path.
It's a chain of trust. R1 trusts R2. R2 trusts R3. If one of those links of trust breaks, the whole thing falls apart.
Second, encapsulation. The fact that the packaging keeps changing. We went from a broadcast shout down a tube to a polite ARP request in a crowded room.
The medium matters.
Yeah.
Context is everything. You don't shout in a library, you don't whisper in a storm. The network adapts.
And third, troubleshooting. That shift from architect to detective.
And that, for me, is the biggest takeaway. It speaks to the fragility of these systems. We think of tech as rigid and permanent, but a network is alive. It's constantly in flux.
And as we saw, you can have millions of dollars of hardware, the fastest fiber optic cables in the world. But if one single line of code, one static route, is missing,
The whole thing is useless, a paperweight. R2 becomes a black hole simply because it was missing one line of instructions.
it's chaos. But the flip side is also true. With just one line of logical code, that IP route command, you can restore order instantly. It really shows you that logic is the ultimate glue holding all of this together.
What a thought. We are all walking on a bridge made entirely of logic.
So for everyone listening, the next time you're sitting there, frustrated that a web page is taking 3 seconds to load instead of 1, maybe take a breath
Give us a second.
and just visualize those invisible handshakes, the routers shouting down tubes, the factory lines stripping and rebuilding packets, the detectives checking their maps. It's all happening for you right now.
It's the silent ballet of the digital world.
Thanks for diving in with us. We'll see you on the next mission.
Stay connected, everyone.